if you're in YouTube land and you don't have a Boost.Stash shirt and you want one, you should be showing up to conferences. There we go. All right, my name is Michael Caisse. I'm with Ciere Consulting. We do, in addition to software consulting, helping people solve problems. We're a group of people who are heavily involved in Boost, and so if you're looking for software of that type of quality and skill level, that's what we do. And we also do training for C++. Some of the things that we'll be talking about today really are the techniques that we utilize internally within Ciere to solve problems. We write things like IDL compilers and other domain-specific languages and compilers that go with those, and a lot of things like that that will lend themselves well to the patterns that we're going to be seeing in this presentation. We'll get a little bit more to where this code came from, but this is less about Boost.Stash. Hopefully that made sense inside of the abstract, and more about what's underneath the hood, and hopefully some techniques and ideas that you can take away for solving problems. Okay, so we'll start off with Boostache, all right? Boostache. Not Boostache, though that is very appropriate at times. That is not it. So for a while, people were thinking, maybe if we just color it, Boostache, then people might figure out how to pronounce it. We had one recommendation that we should make it with a curly bracket, but have you ever heard somebody play a scale on a piano and then not the last note? Yeah, it's kind of irritating, and that's what it feels like to me too. So that's not going to work. This is what ended up on the sign, but I don't know. I don't like that either. The best suggestion we maybe have had so far was Caterpillar. Might as well, right? What else to name it? So naming, we're with Boost.Stash at the moment. This library came about from C++ Now 2014 Library in a Week Challenge. Library in a Week at C++ Now, formerly BoostCon, is a session that begins at 8 in the morning and goes till 9. It runs every day of the week. It's only for those who can get up early, I guess. I don't know. It's a time where we're going to try to develop a library in a week. And there's a challenge that comes from Jeff Garland. He puts it out there the first day. We try to throw some ideas out. And then we just break up into teams, whomever wants to work on it throughout the week. And we just like hash away at trying to get something that makes sense. And of course, it's not reasonable to write a library in a week. But we came fairly close for this one. I thought the group did a pretty good job. And this is the work of that group. It's a C++ template engine is what Jeff says. And we were all like, what? What does that mean? And C++ template engine, what he meant was Boostache is a text template processing engine. So it's going to take a text document and data in, and it's going to produce an output. And so Boostache gets its name from Mustache, because Mustache was the first one that we modeled the template language off of. So you're probably familiar, like Mustache, handlebars, there's all these different things where you take a template that describes what you're going to want the output to be, some data structure, and then you apply those two and get something out. Here are a set of some existing libraries that do this type of thing. This is the original cast that made it through to 8 o'clock in the morning by the second day. There's a lot of people who fall off by that point. Jeff being the one who leads Library in a Week. And there were a few other people who wanted to remain anonymous and didn't make their showing. These were the design goals. To integrate with the STL easily. Type safety. Template parser error handling. Provide customization of markup languages. Make configuration simple. Any data structure convertible to text should work. Some of the features. Compiled templates for speed was a feature request. And there was a design decision early on to use C++11. This is what came out of within the first 10 minutes of people just throwing ideas out. And there had to be a decision made right away. And the decision was, do we force a model on the user? Are they going to use a hash of strings to describe the data structure? Are they going to use JSON? What property tree? What kind of a data structure does it look like coming in that you're going to feed to the template in order to produce your output? Or are we just going to somehow magically accept a user-defined model? Whatever the user gives us, we'll just take and use. And of course, because this is a group dealing with Boost things, we pick this. And we're going to accept any user-defined model that comes in. And we mean any as well as possible. So we're going to see how that mechanism works. That's one of the trickier mechanisms in the system. So here are some examples of Mustache type format so that we can kind of get an idea of what we're trying to do. And here's the template. So the template is hello, curly, curly, name. This will expand to some variable lookup. This is a variable. Here we have this section in which if this is true, it will take this and it'll do something inside here. Here's the end of it. So here's the data that's going to get passed in. We would get name, a value, in California, true, and they have some expression here. And then it prints out this result. Sections can actually relate to a list of items, and if they do, then this section will be repeated for every item within inside that list. So not just a Boolean test, should I take it or not, but also if what it resolves to is iteratable, then we will go ahead and iterate through that. And so here, this repo maps to a bunch of different things, and those things then will be able to be iterated through and pull out name for each of these. And this is the output. So basic idea of what...
It's a spam email generator.
It's a spam email generator, that's right. But we want to do it faster so we can get more of them out there. All right, so let's look and see how you would use Boostache if you were just a user. What would you do with this thing? So the first thing you're going to do, somewhere, you're going to have your template. You loaded it in from file. You've got it as text somewhere. This is ours at the moment. So you can see our double curlies here are going to get replaced then with some data. For data at the moment, we're just going to use a map of string versus string. Well, let's initialize our map. We'll give it a name and an age. We'll get an iterator to the beginning part of our template. And we're going to pass that and the in iterator to this load template, which we give it the flavor of the template, which is stash, is what we call the mustache flavor internally. So we pass it this tag called stash. And out from this, we get this temple. We then call generate, passing it the stream that we would like it to generate to, the template, and the data. This template at this point is the compiled template. And then we pass it our data. In this case, it's this map here. And we just output it or whatever we want to do. Okay? So this will now generate into the stream. So let's take a look at a slightly different example. Input's a little more complicated. It has a section now. We're going to print out some invoice information, it looks like. This time, our data looks a little more involved. We have an item, which is a map of a string to a string, and here's an item list, which is a vector of these items. And an invoice is a map of strings versus item lists. So kind of made a more complicated data structure in order to shove some more information into it, and this is the information we're going to shove into it. So these are our invoice items, like the list of our lines. And then our invoice, we've got lines, and then this thing inside here. So we just kind of set up our data structure to shove into it. Well, what do we do? The same type of thing. We get the beginning and the end of our template. This compiles it. We now have the compiled template out. We tell it to generate, and we just pass in the top of our whatever our data is. So notice we've got now a very different looking data structure that we're passing in. We just pass it in. So from the user's point of view, this is what we want. We want it to look like magic because that makes us feel good. We just want them to be able to pass in whatever data structure they have. All right, let's get a little more complicated. Here's an invoice number, some more sections that we can, if there is a company, we're going to probably do these things, and then some lines underneath it. Now we're going to make this out of an extended variant. So a value is going to either be a string or an object or a list, where a list is a vector of values, these things. So oops, it's recursive, that's cool. And an object is going to be a name versus a value. And so, this is like almost like a mini JSON type looking structure, and we're just going to define it. We don't have numbers, but we've got this now recursive data structure. Extended variant from Spirit looks just like Boost variant, except that Boost variant is not really a type, it's a type def. And this gives us an object to deal with, so we can actually forward declare it and then use it recursively later. So it makes recursion easy of variant types. Now let's just fill this in. All right, so we're going to fill this thing in with that information. If you blur your eyes just right, it kind of looks JSON-y, right? All right. And how do we use this? Like magic. We just drop it in. And it's going to magically somehow figure all this out. All right, one more example if you're not convinced yet. So I have this author thing here and a template. And all this looks the same, right? It's unchanged. Well, what is this author thing? It kind of looks like I am initializing some data structure, and indeed I am. Author actually is just a struct. And the way that we take care of the magic of the struct is we use Fusion adapt struct. What this does is it creates a tuple reference of the things that I say that we would like it to adapt. So this is basically saying author has this field called last name, first name, and library that I'm interested in. I'm not interested in email. I'm interested in these three, and they're of type string. And it's going to, under the hood with some template magic, it's going to create a tuple, a tuple of references to those types so that I can access them later. So if I can be able to detect that I have a tuple of references, or a tuple of any sort, I can iterate, so to speak, recurse, through this thing and then pull data out and utilize it. And if you've not used this facility, it's part of Fusion. Fusion is like library for tuples. You can do the same type of thing with member accessors, getters and putters. And so you can adapt anything you have to look like a tuple. So we've pretty much covered all the types of things that we might be able to see. There's some that we haven't covered yet, and we'll talk about how to extend things. So we can get even more complicated, right? Well, let's just have a company type and a line type, and an invoice then now is an invoice number, and a company is actually, well, this thing, and we've got a vector of lines. This looks more like code we might want to really not see, but it's getting closer. This looks like code now, as opposed to I'm forcing the user into my own data structure. And I just need to Fusion adapt these, and bam, I can just call it. I can pass in an invoice type, and it just works. All right, so this is the magic we wanted to get to. This was our goal. So whether this is here, we're generating this invoice, or we've actually now gone from using Stash, and we just want to use Django's templating format, and we want to actually compile the template using Django type formatting for the input, and we have a compiled part on the inside. So notice that the idea is that the compiled representation is independent then. We can hold these things around. So let's dive into this. What does it look like inside? So inside, we've got the template, the description of what we want to plug things into. We are basically, this is the load template call that you saw. It has a front end that's going to parse this in. It's got a back end that's going to take care of creating a compiled template. The compiled template and the user data are going to be applied via the engine. That's the generate call we saw. And that's going to create the output. So let's look at these different stages. Starting with the first part, this first stream through. So the idea is that we're going to have the template come in. We need a front-end parser to convert that into the front-end AST. So what is the abstract syntax tree, the data structure that represents whatever the format is that came in from Mustache? From there, the compiler doesn't really do anything more than translate one AST into another. That's what compilers do. So we're going to transfer this front-end AST into the engine's AST. And that is what we're going to call then the compiled AST. What does load template look like? Well, load template takes two iterators, or it takes a stream, and one way or the other, it's going to call parse of the thing, and it's passing the result of the parse So that's the AST coming out of the parse. It's passing that into compile, which then is going to result into some AST that's being returned out. Notice this format. Format, well, where is this coming from? Format was what we put into the angle brackets to say that this is Stash or this is Django. And what that is really just a structure that helps us hold some type defs. It helps us put some other types in there so that we can yank them out and do things with them later on. For example, which grammar should this use? Because we might reuse grammars over and over again, or more likely we'll probably reuse ASTs and the grammars might change slightly. What does the skipper look like? What does white space skipping look like for the front end for this versus something else? All right, one of the things that came out from day one that almost made me just fall on the floor laughing was we could use Boost.Spirit for parsing, or maybe a regex would work. And anybody who's ever seen any of my Spirit talks, regex often makes it in there as the ad hoc way to pretend like you're going to parse something. Regex is not parsing. At some point, it falls apart, and you're just like, you have no idea what you wrote anymore, and nobody else does, and it's not maintainable. Regex is great for what it does, right? But if you want a parser, you should probably use a parser, and so we might as well use one. This is what parse looks like. So it does nothing more in parse than start using this format that we passed in to try to figure things out. We're going to get an AST. We're going to get a top node so we can start filling it in. We're going to get the grammar of what the grammar is specified for this thing. And we're going to call into phrase parse for Spirit, giving it the begin and the end, the grammar, what skipper we want to use, and the top node of an AST so it can start filling this thing out. How many people have used Spirit? Okay, a couple people. So the idea is that we want to actually declaratively specify what our grammar looks like. We want to create parsers in such a way that it makes sense and they're easy to read. This is the organization inside of Boost.Stash of the parser for Stash. The AST is going to be what the user of the AST wants. It's like the struct definitions of your AST. AST adapted, we just put the cruft inside there. This is where all the fusion adapt calls end up, macros end up. We just stick them all in one spot for organization. Grammar, this is the lightweight version of the declaration of what the grammar is. The definition is inside this grammar def. This is a trick that we use a lot in Ciere. So Joel de Guzman, who is the author of Spirit, is part of Ciere. And one of the techniques that we use internally is that we would like to instantiate templates somewhere else when we know what the types are most likely that they're going to be used so that we don't keep reinstantiating them over and over and over and over again. And so this is, by separating the two out, this allows us to instantiate something in a CPP file and then not keep reinstantiating it, increases our compile times quite a bit. Decreases our compile times quite a bit. We're really good at increasing them. We want to decrease them. Decrease them. And then we're going to have some printer. So let's take a look at this. Stash parser. What does it describe? Well, it describes a bunch of rules. Rules inside of Spirit are things like this, where we're going to have a nodeless rule and a stash node and an identifier and a comment. These are just the declaration of the rules. And what I want you to notice are these things are actually the data types that the rule, when it's parsed, is going to synthesize. So the parser is going to synthesize a data type. These are the data types. We're just telling you, these are the data types that you're going to synthesize. You're going to synthesize these different data types. We're going to look at those in a moment. That's not the important part. The first part is a node list. So this says a node list is 0 or more stash nodes, whatever a stash node is. Well, what is a stash node? Well, Mustache is either going to be literal text or a comment or a variable that's unscaped, or a section or a partial. Those are the things that make up Mustache. We're going to leave this down here just so that we can keep this in mind. What is literal text? Well, literal text is one or more characters that are not the double squiggly. What is a comment? A comment is a double squiggly followed by a not, followed by 0 or more characters that are not the end, followed by the end. So declaratively, we just said this is what a comment is. In doing this in Spirit, this produced a parser for us to do this, using expression templates. So at compile time, this is producing the parser in a nice way that we can read. It is really cool. I don't know who just said that, but it's really cool. You're right. So here's a variable. A variable is the open doubly, and then this is the escape character that's utilized within inside of Mustache to say whether you're applying formatting or you're not applying the formatting. And then here, there's going to be some identifier, and then the end squigglies. Okay, well, what is identifier? Identifier is, oh, please turn off the skipper. It's an alpha followed by 0 more alpha or numeric characters, potentially with an underscore. What is a section? A section is, it's going to look to see whether this is basically saying it is an inverted section. It's like a knotted section. Instead of the thing being true, if the thing's false, then it takes a section. It's going to have a section begin, followed by, 0 or more nodes, of course, right? Because it's a recursive data structure, followed by the end. The begin looks like this. You've already seen this in the thing. The end looks like the end of whatever the section name was.
Sorry, can I interrupt with a question?
Yes, you may.
Why does section have the modulo equal?
So the question is, why does the section have the modulo looking thing? Earlier versions of Spirit, so this is, I should have mentioned this earlier. So there's lots of us writing code that's going inside of this all at the same time. We all have different experiences. And early versions of Spirit required the modulo equals if you had a semantic action attached. By attaching a semantic action to any of the parsers within would mean that the total expression would not actually synthesize what it was normally going to synthesize, because it would assume that the semantic action took care of it. And if you still wanted it to synthesize it, you had to use this cute little notation. You don't have to do that anymore with Spirit, though.
So why in the beginning do you begin with the LIT and you pass in the double curly braces and then end without it?
Okay, so the way expression templates work is expression templates are basically a data type with an operation between it and another data type. And at compile time, you're building up all these data types. And so you need a data type to try to get things going. And so something has to be, something in there has to be tainted in order to make the operators combine properly. We can't just have, pure literals shifted into a literal. That's not meaningful. We have to somehow taint one of those. And once we taint one, from that point on, we have a type. And so we can just keep using them however we want. Great question. OK, so let's look at what the AST looks like. So the AST, where you're going to use, again, this variant in order to describe things that it could just be one of many of these things. So at the top level, this node is either undefined, or it's a comment, or a literal text, or a variable, or this recursive wrapper to a section, which a section is going to be full of nodes again, or it's a partial. And as we look through this, these are the different descriptions of the ones we just saw. Variable is either unescaped or not, and it has an identifier, where an identifier is a string. So now these are the types of things that you will hear people say never, ever, ever do ever. Okay? So here's the deal. I need a unique type that represents identifier in my system. And guess what? A string is exactly what I want, but I just need the string to have a different type. It needs to just be a different type. So I know that it's an identifier versus a literal text. I'm not adding any methods. I'm not adding anything at all, right? I just need a new type. So that's why we do this. OK. So basic idea of an AST, right? We'll describe a print, usually, because we want to print things out for debug purposes, if not for anything else. We're going to go through how print works so that we can understand how visitation works. And once we understand that, then the rest of it just kind of is going to be a lot easier. So imagine in your head, you have now this abstract syntax tree. You have a data structure that is represented as, maybe a list of things to things that could be lists, that could be things to other concrete types, like maybe a string or any of those things that we just saw. And so you've got this tree. And now you would like to walk this tree and print the values back out. What do you have? How we do this is we're going to take a stream in, a reference to a stream, and we're going to take the node list. This is the list of nodes. This is the thing that we parsed. It's the very top level. We're going to take that and pass it in. Well, what are we going to do first? Well, we're going to just iterate over the nodes, all the nodes, and we're going to apply a visitor where we pass the node that we currently have and the visitor. We're going to talk about what the visitor is now. The visitor is, in this case, we're going to look at printer. The visitor is nothing more than overloads for the operator, for the function operator, for the callable operator, my goodness, for the callable operator for every type that could be inside of our variant. Right? So every type that this possibly could be in our variant, we're going to have an overload, undefined. Okay, we're going to print out, whoa, we are undefined. Comment, we don't really care about printing out comments, so we're not going to. Every time we see the literal text, well, we're going to actually just print out the literal text. When we see a variable, we'll put the squigglies in front. We'll look to see if it's escaped, because if so, we can put the ampersand, then we'll actually put out the value that was there for it and end it. How about a section? Well, a section is a little more complicated. We're going to have to put squigglies. If it's inverted, we get one of these. Otherwise, we don't. We're going to put the name out in the end. And now we're going to iterate over every node that's inside of the section. And we're going to reapply the visitor, right? Because we don't know what the type is, so we're just going to keep applying the visitor again and let the visitor take care of the problem for us. And at the end, we'll stop here. Now, this is a good place to stop and think about what we've just done. We have a pretty complex data structure. It could be a lot more, but it doesn't matter how complex it is. We're dealing with one small part at a time. Conceptually, we don't have to think about the entire world. All I have to think about is, what do I do with a section? A section has this introduction, it has an ending, and in the middle, I don't know, they're just nodes like everything else. So what am I going to do? I'm just going to dispatch to the thing that is handling the nodes from the top in. No reason to think about it, right? Okay. We're going to use this concept a lot. So we've now got a front-end AST. The parser code that you saw up there, that's it. It creates the parser for us. We don't have to write any more code. Can you imagine writing code, whatever it was, you would have written the code half an hour ago in order to parse that in? It's not a horrible grammar, but I bet you would have had a lot of code and a lot of bugs. And it would have been hard to think about procedurally. We just declare what we want with Spirit. All right, so load template. We're finishing up this. And now the result of this is that AST, we're passing it into compile. So what is compile? Well, compile is going to, first, compile here is taking the output of this, right? And that output was the AST that's associated with the input grammar. So Mustache has an AST, something that's going to describe it. So how do we now take then that stash AST? Well, we're going to take that. There's an overload for compile that's going to take that type, and it's going to call the compile on the AST for the stash compiler. What does that look like? Well, you bet we're going to do visitation. So we're going to visit the AST. So what does the visitor look like for the AST? This time we're not wanting to print things out. We're wanting to take the AST in and transform it into a different AST out. That's the compilation. All right, so coming in, we've got our root. And the root, the top, is going to basically be a node, a list of nodes. We're going to iterate over each of those, just like we were before. And we're going to take the node list. So we have a new node list. This is our internal, the virtual machines AST. We're going to take a node list of that, its nodes, and push back the result of applying the visitor to the node I have. Right? So I've got a list of nodes. I don't know what the result is. I don't care. All I just know is that whatever it gets back out in the transformation is what I have to push on my new list to make new ones of these, new bits of these. And then I'm going to return the node list at the end. So what's inside of the VM AST? What are we transforming into? Again, undefined. There's a no-op, literal variable. There's a render. There's a for each, an if then else, a select context, and a node list. These are the intrinsics of the internal language, basically. And everything that comes in from any other template type has to be transformed into one of those intrinsics. Not super important what each of these are. You probably can guess what most of them are. Literal, the for each will have a name associated with it and a node. The if then else is going to have a condition that'll be evaluated, and then a node on the then and a node on the else, right? Which are basically like lists of what to do. All right. So how do we transform undefined? Well, an undefined is just a empty node. What is a literal text? A literal text, we can just return internally our literal, because that's what it is internally. What is a variable? Internally, that's a render. So generate a render data type and return that. Notice each of these are returning node. Node was our variant type. So that variant type can hold any of these. Comment is a no-op for us. We don't care about comments. A partial. Partial is currently a no-op because they're not implemented in this version that's on the slide. They're inside of a branch at the moment for partials. Partials are ways to include other files. Think of it that way. It's like an include, which is a little more complicated how we want to reason about them. We want to do something a little bit differently in the library. A node list. Well, what is a node list going to convert to? A node list is going to convert to just another node list, right, of the AST node list. But see how I can just reason about this? Well, what is a node list when I convert a node list from one type to the other? It's just the node list of the internal data type instead of the one that I read in. So I'm just going to keep calling apply visitor and let that take care of it. Let's get to something a little more complicated. A section. So a section, it's going to look at the node list, at the nodes, and push those back. So for this section, when it comes in, the section has a bunch of nodes underneath it. And it's going to transform all of those nodes, each of those, into a list. And now it has them. And once it has them, it's going to, they're going to be in this VM AST. It's going to get put into the section body value here. We're going to create this internal for each, and it has the name here. So for each, this is the value, all the things that we just took care of, and then its name. And Mustache is weird. Its sections are both a condition test and then a loop. So we're going to have to form inside of our internals a conditional test, whatever that means, and a loop. So here we produce the loop, the for each, and now we're going to produce then an if block where the condition name is the name that came in from the section. We're going to select the context. So selecting a context basically means on the data side, we're going to move down a level on our branch, give it a name, and then assign the section body to the body. And then we're going to check, is this thing inverted? If it's inverted, then when we do the select, it's going to go into the else. And if it's not inverted, then it's the then side. So we just can pick one way or the other. So this is the most complicated thing we have. And again, I didn't have to think about it very hard. I just had to think about, in terms of a section, what are the mechanics of a section? All right. So we now have moved from our front-end AST to our engine VM AST.
Sorry, the last one.
Yes.
What is the definition of select context? What does it contain?
OK, so the definition of select context, then, what does it contain? Select context has a tag and a body. And we're going to actually spend some time with select. So we'll see in a little bit the complexity that exists with select. All right, so if we have multiple front ends, we have Stash parser, we have a Django parser. We don't have any others at the moment. But adding new parsers is simply writing that declarative Spirit grammar that reads it in, and then now you have whatever the natural AST is for reading that in, and then converting it using one of those compilers. And you can see the compilers aren't that really hard to write, right? It's just how to transfer one AST into the intrinsics of the internal AST. And now we have the engine AST. So these are how all we can support the multiple front ends. We're going to move on past the Django example for now because we don't have a lot of time left. So let's look at the generation side. So we've completed this. We have a compiled template, and now we're going to pass that in along with the stream that we want to output to and our data at the top. We're here. That's what we're trying to do now. So what does generate look like? Generate took the stream, it took a template, and it took what we're going to call a context. We're going to call the input data, AST, we're going to call the context. And we're going to use that to refer to where we are in the AST actually at any point in time. Initially, we're at the top node of the AST, at the very top. The detailed generate call looks like this. It is going to get an engine. So it's going to construct an engine based upon the stream and the context. It's passing those in. And then it's going to call engine passing it the template. Notice, what is the engine? A visitor. I have an AST that perfectly describes exactly what I want to walk. How do I walk that? Just with a visitor, right? There's nothing complicated about this. Well, almost. The walking part's the easy part. The data side is going to cause us some problems. So let's say I have a data structure that looks like this. It has a conference, and conference has a name. It has a conference data type, and within the conference, inside there, it has a name, and the name is Jeff. It also has this year, and it has conference has a name, and it has a CppCon inside there, and it also has a year object. This is like pointing to an object. It has a year 2015. So I'll try this again. I've got like an object that has a conference thing in it and a name. And name is pointing to Jeff. The conference is pointing to this thing. And what is a conference? A conference has a name and it has a year. The name is pointing to CppCon. The year is pointing to 2015. My AST that I just read in that I'm just getting passed into the engine, it looks like this. A literal, there's an if condition, there's some things going on here. Let's walk through this. The if condition is going to start here, and it's if condition. And it's going to do whatever the test tells it to do. And if the test then is true, then I want to actually descend on the data side. So you remember before with the select bits and pieces, with sections in Mustache. In sections, once I actually selected that object, it existed, it had that type inside of the map, I actually want to descend into whatever it was referencing. So a map of string versus like another object, if that is in there, then now over here is where the context is. We want to move over. And so if it's true, then I want to select the context, which is selecting on over here. And now I can do my literal render, and I'm going to render whatever it is. So the idea of what we're about ready to talk about is as I am moving through and dealing with my AST on this side, the instructions, I actually have to, based upon whether I'm selecting context or what else is going on, I have to be at a different spot inside of my data tree. And so select context is going to basically move me about throughout the data tree. Okay. So what does an engine look like? So here's the visitor for engine. If I have a node list, which is what I start off with, I'm just going to iterate through all the nodes, and I'm going to apply a visitor on the node, right? Woo, easy. All right. If I have a node, somehow I actually have a node itself, what am I going to do with the node? I'm just going to apply the visitor to the node. Because remember, a node was a variant type. It contains one of a bunch of different types. I don't know what type it is. So I've got to strip out the type that's inside of it and then revisit it. What are my types? Undefined, I'm going to do nothing with. No op, I'm going to do nothing with. A literal, I'm going to render. I'm going to call this thing render, passing it the stream and the literal value that I currently have. This using trick here says basically grab whatever the default renderer is, but if the user overloads render for their own data types and value types, which they're going to be able to do through an extension mechanism, it'll use that through ADL. So this is the trick in order to get us ADL lookup. We'll get the version that comes with Boostache unless the user has provided an extension for it and they want something else. We use this over and over again. So here's just the render method. If then else. Well, what do we do with an if then else? We're going to call test, passing the context and the condition name. And if the result of calling test results in true, we're going to then apply the visitor to the then side. Otherwise, we're going to apply the visitor to the else side.
So it has to look at the type of the literal value, for example, in this case. So the user and you will have to agree on the type.
It has to look for
lit.value or r.name.
Yeah. So we'll talk about the extensions in a little bit. So the question basically is how we're going to all have to agree on a type. How are we going to agree on that type? And we'll see how we're going to agree on it in just a little bit. We're going to agree because I'm going to tell you what the type is. All right. All right. So what is a for each? A for each is just calling this for each, which seems pretty innocent at first. And now let's take a look at what for each is. For each is going to take the stream and the node that we got and the context. And the first thing it's going to do is it's going to actually just dispatch another call of for each that takes 4 parameters, where the 4th parameter is this thing called the for each category given the input context. So the input context at this point is a data type, right? It's the data type that the user gave me. I don't even know what it is yet. This is what I'm about ready to try to figure out. How do I deal with the type that I have? And what I'm going to do is I'm going to say, what is the category? Can I categorize this type that I have and make any meaning of it at all? And this is going to result then in some type. All right, what are the categories? Well, we just kind of came up with some categories. These aren't well-designed categories. That's what happens when you do a design in a week, right? So the categories that we have right now that seem to make sense initially for writing this and making something work is we have an unused attribute, a plain attribute, a sequence, associative, tuple, variant, and optional. The belief is when we entered into this is that most things seem to fit into one of these categories. And if they can fit into one of these categories, we understand what to do with the categories. We know what to do with an associative container when we see it because we can actually switch contexts with inside of them. We know what to do with a sequence if what we're supposed to be doing is a for each loop. And it models the concept of a sequence at that particular time. We know how to test something for Boolean trueness given the category type. So categories tell us everything we need to know about your type and what to do with it without me knowing what your type is to start off with. So at compile time, as you can see we're getting ready to do now, at compile time I'm going to determine what to do with your entire AST and the types based upon the category. So let's look at some of these. For each, you don't care about any of these, really. Well, okay, this is the magic. So the for each category starts off with a plain attribute. This is the default one. I put in something, I put in anything for a T, I get a plain attribute out. I'm going to specialize it. I'm going to treat strings as plain attributes. We'll see why in a moment. I'm going to treat, using an enable if the thing I have is a variant, because I can have boost variants, I can have spirit variants, I can have all these different things that look like variants and treated like variants. If it is one of those variant type things, it looks like one, then it's a variant attribute. If it is a sequence that's not a map, because I don't want to treat maps like sequences, I want to treat other things like sequences. Sequences for me in the for each sense of the word, because notice I'm in the for each category right now, I'm not in one of the other categories. In the for each category, I want to say that maps don't look at all like a sequence. Instead, maps are going to look like an associative thing to me. That's what a map is going to look like. If I have an optional, it's going to look like an optional attribute. And then I'm going to use a template alias just to make my life easier so I don't have to write stuff over and over again, right? All right, we made it this far. We've got now the for each that's going to take any category that comes in. And by default, what does it do? Well, if it's not been specialized, what it's going to do is it's just going to call generate, which is, and it's going to pass the stream, the current node value that it has, and the context. This was the top. This is where we started this whole operation from. So basically, I'm going to say, if I get to this point in the for each, I'm just going to call back into the very top entry with what I currently have, and now let it work its way down. I don't have anything to iterate over, basically. What do I do if it's a variant? If somehow what I have right now is a variant, it is completely useless to me. But what isn't useless to me is the thing that's inside, that's wrapped up. And so what do? I create a very special variant visitor, which is not so special, which is going to unwrap this variant for me. So unwrap variant for each, which is just this. It is going to simply create this type, giving it the stream of the node, so it's storing the state basically of where I am, and calls the variant, or calls the apply visitor, which for whatever type it has, now it knows the type, it can recall the for each with the correct type because it's unwrapped it. So it's done nothing, right? It's just basically calling for each again now that it actually knows the type that's inside the variant. Eventually, we're going to get to do some work here. Optional's not it either, because I don't know what an optional is either. I have to test if it's there or not. If I have one, well, now I can actually call the for each with the thing that's inside of it. So I pass it, I dereference it, and at this point, actually, what is the for each category based upon? It's not based upon the optional, it's based upon the type that's inside of the optional. So I use decal type to ask what's inside there. Otherwise, I just call generate, move, I just move on. Okay, finally we have a sequence, something that we can iterate over. I go ahead and call, wow, what a surprise, generate over each of the nodes that are inside of the sequence, passing it now the node value and the item. All right, so let's think back up to the engine visitor. So that was the for each, pretty easy, right? Really, because I'm just calling back into myself. I'm only handling the special cases and where I know what to do with. The other takeaway here was the category thing. If you can categorize types of things you want to deal with and deal with them generically, then you just have to worry about how to classify them as a separate exercise. All right. Select context. This is the trick. This is one of the tricky parts. So select context, the idea is that we have now this idea that I checked, it has a company, and now I need to now move over inside of my data structure to where the company is and start working with company. I've got to select that within my data set. So I call it, and hey, this looks familiar, right? I want the select category context this time instead of the for each context, and I'm going to pass it now. So this allows me to deal with categories based upon the behavior or how they're going to be used. Not just all of them are the same, right? All these things look like sequences always. Well, no, not necessarily. Sometimes these things look like sequences when they're being used in this realm, but other times these other things look like sequences depending upon how they're going to be used. All right, the dispatch, what a surprise, is going to just call generate again if it doesn't know what to do with it. So that's always what we do. If we don't know what to do with it, we just call generate. Here's a version now where it's an associative attribute. Associative attribute means that I now have tested the thing, it's true, I've got this thing, I can now select the context of whatever it was supposed to allow me to switch the context for. So how does this work? It's assuming that there's this find for these associative things. If it finds it and we're not at the end, then it must be there. And now I can call this select context, passing it now the stream, the template body, where we are inside of the template itself, the context, and the second, so the thing that it pointed to. And now notice when I call it, I'm calling it with the type. The select category is now the type here of whatever is pointing to. Because if you have an object of objects of objects of objects, you don't really want to be on the outer shell. You need to descend all the way down until you get something concrete to work with. So a map of maps of maps of maps, you need to be at the lowest level of that map to do something with it. We found that because it didn't work the first time. But it was an easy fix. All right, what does select context do? Well, it just calls generate. Unless it's an associative attribute, in which it calls generate. Because an associative attribute means that we need to do this thing again. And when it calls generate, instead of passing in the parent, it passes in the child. Because now it's going to basically run the same thing on the child and descend back down. How about if it is a sequence attribute? Well, we're basically saying that what we've pointed to is an array or something that we can iterate over. Perfect, let's stop there and call generate, passing the child in. What if it's a variant? You know the answer to this. If it's a variant, we don't know what to do with it, so we have to unwrap it. So we create an unwrapper, which did nothing, if you remember right, except for take the type and recall back in. So it's redispatching back in. All right, so without probably too much imagination, you can see how working with just one little chunk at a time and by category and by type, we can do just about anything that we need. And what did we just do? We just took any type that you give me that I might happen to be able to distinguish and figure out what the category is, I can use it. How does it figure out what a sequence is and why do I remove map? It figures a sequence out by determining whether or not it can call a begin passing it that. If it can call begin passing it the type you give me, it figures out I can iterate over this thing. I don't know what it is, but I can iterate over it. And it just uses that. So by understanding just some basic things of the types that you give it, it can make decisions and you can give it any data structure. But what if you give it a data structure that it doesn't know what to do with? It can't figure it out at all. So here we have some input and template. And conference started is going to be a lambda that happens to always return true. The topic is going to return Jeff's latest issue at the moment. And now I have this thing, this S model T data type, that is going to take a string on the left side and, oh my goodness, a callable lambda thing on the right-hand side, right? Okay, we haven't seen any category that this is going to be able to deal with yet, right? We don't have this mechanism inside of Boost.Stash to deal with callables. It doesn't know what to do with them. And it doesn't know what to do with them on purpose, by the way, because it doesn't want to just go around calling things. You may not actually have meant that. But I can tell it what to do. I need to tell it two things. Notice this. It needs to understand when it hits this section, this is testing. It's testing whether or not the thing is true. And it would have done a for each if the thing was, it could be iterated. It also, name, it needs to be able to somehow render the thing. So those are the two things it needs to understand. What we're going to do is inside of the Boost.Stash extension namespace, we say test, giving it the things that test normally gets, except for here, the context type is going to be any callable function here, a null array function, and we say it's a plain attribute. So the plain attribute then, when it is this, because it's going to be a plain attribute because it doesn't match any of the categories we have, so therefore it's a plain attribute. And we've now overloaded it for this function type, right? So the signature is going to match. When you see this, return, and we're going to call test, passing it the name, and in this sense, we're actually going to call context, because we know this thing's a callable that came in. So we're just going to call it, and we're going to pass the result to test within this context. So if if it returned a map or something, it would just do whatever it was supposed to do with maps, right? In essence, what I'm trying to tell it is, this is how you're going to extract the information that you want to continue passing on. I could have just returned a Boolean at this point. True. This is how you deal with Booleanness. If I wanted to overload the render, same type of thing. Here's the function that the context is being passed in, and I'm going to call render, executing the context, passing that result into render. And so this is how the extension mechanism works. And as you can imagine, without too much thought, just about anything you write, then you can therefore write an extension for it. There's 4 extension types. There is the test, the render. No, there really are. Oh, there's a for each, and a context. And a context. There we go. So if you have complications with any of those, you can write then the extension for them. So what's the plan for the future?
Michael, one more question.
Yes.
So could you use this mechanism to start plugging in stuff into the AST? So if you had an include could call one of these, would invoke one of these extension functions?
Yes. So the question is, can you use extension functions to actually do includes? There is an individual in Italy who's been using Boost.Stash quite extensively, and that's what they do in order to handle weirdness to plug things in. What we're trying to do is actually to come up with a reasonable extension mechanism to let you include things into the AST when it sees events. That makes more sense. But yes, you can use the extension mechanism for all kinds of abuse. We need to complete the Mustache and Django support. In particular, what's missing are partials, which is that include capability. The other weirdness, you saw how we kept basically diving down into the data structure that the user gave us, the context. What we're going to need to do is write a context that basically is the same type of design that we use in Spirit. And it's a wrapper that's going to go around what the user gives us. Because not only do I need to be able to dive down, but if the user says up here is name, and we've gone down into the data structure, and they suddenly use name, it has to actually look up until it finds something that says, ooh, there's where name is, and use that. And we don't have a way at the moment to go back up. It's not trivial to do elegantly. And so we know how to do it because we've done it in Spirit. So that's the other thing, major thing that's missing. We actually need to complete generalizing the category handling and actually design it properly instead of kind of what we did in a week. And flesh out the extension mechanism so it's fully defined and specified. And then we just need docs, lots of docs. There are a few people who are using it. We're getting bug reports and feature requests and pull requests for actually new features and stuff. So it looks like there's some people. So. All right, you can find it here. Ciere Labs is open source effort by Ciere to stuff that we work on and do, and we just throw out those YAML parsers and JSON parsers and other weird stuff out there. You can find the project there. If it's interesting to you, please get involved. Hopefully this was a useful talk for you to kind of see how you can use these different techniques internally and to reason and to think of things in a way that are really smaller chunks. Try to contrast that to what you might have done procedurally in order to write this whole thing from beginning to end. All right. I think we have like no time for questions. We have 44 seconds for questions. Oh, Ben?
How do you detect maps?
How do we detect maps? Right now, we detect maps simply through matching on STD some type. I'm sorry, STD map. So we only detect STD map.
Oh, okay.
Yeah, so if you had another type, you'd use the extension mechanism, and you would say, let's say it's a type for an associative. So you would say that on a context switch, you would want to add into the category your type that is now, your type is now an associative type. And that's like, if depending on how pretty you want the line to be, it's 2 lines. If you don't like pretty, it's 1 line of code. And then that would mean your type is now an associative type. It would understand every time it saw that, it was associative in nature, and therefore it could do context switching on it. Now, what context switching means on it is a different question, but you could write the overload for how to get the data back out.
Right. So you can plug in, the tag dispatch would work for your type.
Yes, the tag dispatch would then work for your type. Right? So it generally will understand, because of the mechanisms there, it basically will understand everything that's out of the STL container types. It understands a lot of other types. It understands tuples, which suddenly opens the world for all kinds of weird things. It understands all the fusion types that exist.
So the engine AST, could you use it without the front-end part of it? Because that'd be a 4-man boost automatically.
Yeah, so the comment is that you could kind of use just the back end as a poor man karma. Yeah, you basically could.
Is it packageable that way?
The back end is in separate directories. Yeah, it's not tied to the front in any way. Yeah.
I'm just wondering what kind of error detection, or what does it look like if you type the wrong name into a template or something?
Yeah, so that's a great question. So if you type the wrong name into a template, and it's important to you that it finds that, you should talk to Roland, because Roland actually has a template engine that parses, that utilizes the template definition bits inside of the compile time. And so it can do compile time checking, type checking, in a sense of you meant or didn't mean that thing. And so you should talk to him. In Mustache, what it means is nothing, do nothing. So by specification, it means you asked for name, I don't have a name, I don't want to output anything. That's what you mean. And so it doesn't output anything. And most of the template engines, that's how they behave. When you see something, when it can't find something, it just continues on. Now, one of our users has requested that once it goes through all this work and it can't find anything, that you can provide a handler, an optional handler that would tell you that it can find. We've got thumbs up going on over here too. Yeah, so that's trivial to do, as you possibly could imagine where in these trees to put it. It's like very trivial to put one in, and so that probably makes a lot of sense to stick one in. Anything else? All right. So our time is up. I'll be around if you have further questions. The slides will be uploaded. The bonus slides that follow after this show how the metaprogramming works in order to descend into tuples, if you really are into that type of pain in your life. So you can watch that. Thank you very much.